So the hunt for this rest part was on, what it was consisting of, and Thomson thought, well, if this whole atom is neutral and electrons are negative, then perhaps the rest of the atom is a sort of positive liquid where the electrons describe, well, in fancy patterns they describe fast orbits through this positively, well, charged liquid. And the patterns are here for 1, 2, 3, 4, 5, 6, 7, and 8 electrons. 9 is probably too difficult, I don't know. And they were rotating. They're not at a standstill, they were rotating, but at a really high speeds, almost 10% of light speed. And it was later called the plum pudding model. So the British dessert plum pudding basically is not a pudding, it's sort of bread thing, and there are not plums in it, they're raisins. So I can't help the name, but it was called the plum pudding model. In Dutch we have a similar thing that looks like this. But basically this is the model that they have had, that Thomson's model was of the atom. And then of course the raisins here are the electrons, and they were moving through this atom in high speed. Now if this is your model, then you can do experiments, and basically if you shoot positive particles at these atoms, then perhaps they might move through, but the whole model is a neutral atom, so basically they would move roughly straight ahead. Now, if you do this experiment, then you expect something like this. So you put up a gold foil here with lots of large atoms, you shoot these alpha particles at them, and roughly most of them would go straight ahead, and you would detect them here. Now, of course, Rutherford had an idea that perhaps it's different. So he did this measurement, and they found this, that yes, indeed, most of them went straight ahead, but some were deflected, and some were deflected at a ridiculous angle. So almost they bounded backwards. So that meant that the core didn't look like this, where most of them went straight ahead, but more like this. Where, yes, some of them went straight ahead, but some, if they are directed exactly at the center of an atom, then they might bounce back all the way. And that meant that the atom core, basically all the positive charge is concentrated in the nucleus. And that was the new atomic model. So a positive nucleus in a very tiny area, much smaller than this drawing actually, with the electrons in a negative cloud around that. That was the discovery of the nucleus, which is not an elementary particle, but we're getting closer. And the hunt continued for, well, the parts in this nucleus, and they also did experiments with anode rays, so the positive rays, and they already found that you can have positive gas ions in this ray, and they found that hydrogen ion has the largest charge to mass ratio. So basically, if all the gas particles have the same mass, then hydrogen has the largest charge, or if they all have the same charge, hydrogen has the lowest mass. And basically this was the case, had the lowest mass. And Rutherford did these experiments, and he shot these alpha particles at air first, and he knew air was consisted of particles, and then he used pure nitrogen, and then he got a bigger result, and he produced these hydrogen ions in this reaction. It's not a chemical reaction, it's a physics reaction, a nuclear reaction actually. And it was the first reported nuclear reaction. So we have this nitrogen with this alpha particle, which is a helium, doubly charged, doubly ionized helium atom. And then it produced this isotope of oxygen and the hydrogen ion. So in the picture it looks like this. So basically he created the first hydrogen ion, which was basically the proton. So the neutron took a while longer, but you can imagine that because a neutron is a neutral particle. But they thought of that because you saw in radioactive decay, you saw electrons coming out of the atomic nucleus. Now, if an electron comes out, basically that means if it's in there, it's neutralized by a proton. So you can imagine that this neutron thing that you're looking for, because the mass wasn't the same as just with protons, that the neutron is a sort of combination of a proton and an electron bound together. So this was the idea that these two together form the neutron. However, if you try to make a particle of an electron and a proton in this very small space in the atomic nucleus, that means the electron has to go to ridiculous speeds, and basically that's quantum mechanically impossible. So that's really a bit of a problem, but still James Chadwick did experiments, and he found that there wasn't basically a set of two particles connected together. They were single particles, and they did this experiment with a polonium source, so that's a radioactive element. It gave off alpha particles. He hit this beryllium plate, and out comes this unknown particle radiation basically, and that hit a paraffin wax layer, and out come protons. And you can do measurements on the protons and then find that basically these particles, neutral particles, have roughly the same mass as those protons. So he found the neutron, but that's only in 1932, so many years later. So he found that these are separate particles. And basically with these three particles, the electron, the proton, and the neutron, we can build atoms. So in fact, atoms have been explained this way, and this is also what is being told in high school still, and we can build atoms from that. So yeah, we can sort of party, and everything is done, right? Well, wrong. The work's not finished, really.